Uh, Welcome back, and we have today the final Madhava lecture by Professor Divakaran.
Good. I'm sorry I messed up my last lecture a little bit. I hope it doesn't happen today. I'm not going to derive, except one little thing, I'm not going to derive anything in detail today. I'm going to describe to begin with, I'm first going to describe what is the formula at the discrete level which becomes the solution of the integral equation for the sine function, the series. There is a finite discrete description of that situation, and that's I'm going to write down. I'm not going to do it, and because it's a very interesting thing in itself. What will happen is that the multiple integrals in the integral equation, they will, and in its solution, will all become multiple sums. And in the finite case, they're not infinite sums, they're finite sums. So that's the formula I'm going to write down. And Yukti spends a tremendous amount of time explaining in detail how it is done. It is, in modern notation, it's very, very hairy because there are all these multiple sums with different ranges of for the indexing quantity to sum over. And the result is this. That is, what I have in mind now is an arc of a circle subtending an angle theta, and I've divided this into 2n equal parts. 2n because I don't want midpoint complications in the notation. And the difference is defined as the difference between not two neighboring values of the function, but with one step separated. That is, the function at I plus 1 minus the function at I minus 1. That's how I define the difference. It's very, 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 it simplifies the notation enormously in the actual writing. So I'm going to use this part of the blackboard today, and when the time comes, which is will be twice today, I will use the blackboard. I'll use the screen, but very, very, very infrequently, so it will not come in the way. The solution of this discrete difference, the difference equation, or equivalently the discrete integral equation, is a formula for sine theta in terms sine theta divided by 2n. Since I said that I've divided the arc into 2n parts, that's how it comes. And this is the formula, which will, it's not logically very complicated, but actual writing it in terms of lots of indices will come and so on and so forth, complicated. So it's the formula, sine series for discrete differences. Sine theta. Is this big enough, the writing at the back? A little bigger. Yeah. Is first theta divided by n. It's a common factor. Then I'll define these quantities in a minute. S naught n minus 4 sine square theta divided by 2n. S2 at the value n minus 1 plus 4 sine square theta divided by n to the power 2n square S4 n minus 2 and so on. As of now, I have to define what these coefficients are, S's. They're defined recursively. They're defined as sums of sums. So where Ski is defined as I j from 1 to I of fk minus 1 j. Okay, so that is, if I know the values of at all j of sk minus 1 index lower, then I can determine the general term in terms. This comes from the use of the finite difference finite fundamental theorem, as you can imagine. It's always the same trick. You write a quantity in terms of differences of or the lower degree objects, then you take the limit at the end. Okay, where is, I don't have to say. What is S naught n? S naught n is 0, L is 1. S naught n is defined to be 1. The initial values will have to be specified. S naught n is 1, and sk naught, what is sk naught? Let me see. K, ski is I. All right? Sorry, not 1, 0. Sk naught is 0. Sorry, I beg your pardon. Then, so you can write this, you separate the first term. What do you get? Take the leading term out, S k minus 1, I minus 1. That is all the terms except the ith term, plus, sorry, sk minus 1, I. So this is recursion relation for the coefficients. They are defined in this way. Now what you can do now is to solve this recursion equation in many different ways, but the modern way would be use induction on both I and k. It's very straightforward. It's not difficult at all. It's very straightforward. And I'll make some remarks after I write the formula down. These are actually binomial coefficients. The quantities sk, I are binomial coefficients. In fact, sk I is I plus k factorial divided by I minus k plus 1 factorial I minus 1 factorial. This is the same as I plus k combinatorial coefficient I minus 1. What is it? K plus 1. Yeah, that's what it is. This solution I'm not giving. It's not very difficult. It's quite straightforward. I will say something about it though. This is the way these coefficients come in this particular derivation because of the multiple sums. However, exactly the same problem occurs in a combinatorial context about 1500 years before Madhava did the work. 2nd century BC, Pingala, in his classification of metrical structures with 2 variables, Laghu and Guru, one of the problems, the last problem he poses is, what are the number of distinct sequences in X and Y in which the total length of the sequence is fixed and the number of times one of them occurs is also fixed. Total number is the equivalent of I here, and the number of laghus which occur is K. You get exactly the same formula. And this is actually very beautiful work, a modern historical work by Jayant Shah, whom many of you know. Pingala's work was reinterpreted in many different ways by many different people. Then, I'm very fond of this story. Then Jayant Shah looked at it. Then he said, if you want to understand Pingala, you must read somebody who lived 100 years later, Bharata, the Natyashastra specialist. It's an example which I like very much because here is, combinatorial mathematics moving in step with music and dance. It's wonderful, very, very great story. So what Pingala did was to construct these binomial coefficients, starting with the lowest values, k equal to 1, I equal to 1, and building up. That is effectively induction without stating a general rule for general K and general I. He just built it up. He said, he gave many examples. So that is the story. This is the sine series. Now all you have to do now is take the limit here. Now this will end. This series will end. No, this one will end after some time. Why will it end? Because one of these coefficients will become 0 after that, and it's very easy to see. Yeah, what I want to say now is what? Oh, take the limit and go into infinity. Look at the corresponding limits in the coefficients. Look at the way these powers of sine theta by 2n change with n, and you get the sine series. Madhava sine series, Madhava Newton series. Okay, we stop it here. That's it. I don't want to say do more. And the fact that you can do it extremely, almost trivially, by writing the integral equation directly. I was very happy when I first found out for myself that it can be done. Then I discovered that Whiteside, Newton's editor, actually in a footnote to one of Newton's papers, says that I understand that a mathematician called Nilakantha in Kerala has found the sine series by this method, integral equation method. Of course, Nilakantha was not the right person. Madhava was the right person. Madhava's name doesn't occur in any of Whiteside's writings. Okay.
Is that first line equation as it is written, or is it supposed to be read as a limiting line?
Oh, here. This is an identity for any n. This is an expression for sine theta in terms of theta divided by any positive integer. Simplest form of this will be sine 2 theta is 2 sine theta cosine theta. That will come. I mean, it's very straightforward. So this is an identity. What Yuktibhasha does, I should say that Yuktibhasha doesn't write this identity anywhere. Long ago, long before all this, he has already replaced sine theta by 2n, sine theta by n by theta by n. He's already done it, delta theta. So sine by the angle, I beg your pardon. Sine is small angles by angle, theta by n. So for him, it is a problem in the limit. Unlike the tangent series, you can't do that because those Bernoulli sums are not easy to handle. This is very straightforward. It's very easy. Yuktibhasha doesn't give the proof of this formula, by the way. Shankaravarya, who mentions the same formula, says that the proof is too difficult for people to follow. So I won't give it. Alpadhyam hita, he says. The people with small brains won't follow it, so I won't tell you what it is. So he says, the reason I think is that it does involve double induction. You have to do the induction in both I and K. That's what I think. Anyhow, there we are. But neither of them says that this formula was known to Pingala in a different form. So following the historical development, something which Spenda I talked about at lunchtime today. It's an absolutely fascinating thing to do, to trace the ideas back to where they came from. And there is no mention of Pingala. You know, it's as though the mathematicians and the combinatorial guys, like Sharangadeva or before that Bharata or before that Pingala, did not talk to one another, except to some extent Bhaskaracharya, but to a greater extent Mahaviracharya. In the Ganita Sangraha, there is combinatorics. Varahamira before that. So that is the department of the musicians and the dancers and the poetry makers. This is serious people doing astronomy and similar things, you see. So that is that. Now, I'm going to change the subject. I'm going to deal with a problem which is not vitiated or does not have the confusing presence of infinite series. So you don't have to worry about whether infinite series can only come from calculus or not come from calculus, which has caused a great deal of confusion in the writings, modern writings. This is the surface area of a sphere. Okay? It is done this way. I'm going to avoid this part of because I'm going to use a screen. I have the sphere. Says first draw the east-west line. And the east-west line is what we will now call the equator. Why don't I? Where is our man? There. Can you pull the screen down? I'll talk while you pull the screen down. So you draw the equator, draw latitudes parallel to the equator, infinitesimally separated. Where is the pointer? This is from the last lecture. So I'm going to, what does it say? Through the middle of the sphere, imagine drawn two circles, one along the east-west, the equator. Oh, I still hear it. This is the equator. And the other north-south, which is any meridian. And that for me is this. Two circles. Then it says, imagine two circles, one slightly to the south, the other slightly to the north of the equator. These are parallels very close to the equator, latitude parallels very close to the equator. These two will be slightly smaller than the first one. You know, I show this because this is the way they actually write. You know, I chose a particular example because it's very easy to follow. When you have complicated formulae, it's not easy to follow. But the text is very clear. There is no confusion about it. The separations along the meridian should be equal. What does that mean? It means that if I make two such parallels, or another one here, they are equally spaced in terms of the angle subtended at the center. That the arc lengths are the same. This is important because in the volume formula, what is equally divided is not the arc length, but the length of the axis. That is equally divided. The two are different. And the calculations actually depend on the simplicity that this particular choice of infinitesimalization brings into the problem. Then, what does it say next? Imagine that the circle-shaped annular gap between the two, typo. Successive circles is cut at one place. That is, you take this strip, the annular region, which goes around like that, cut at one point, then removed, that is, you're assuming that you've got a surface which can be removed from the surface, remove it and straighten it. When you straighten it, what do you get? You get what it says, a trapezium, symmetric trapezium, in which this side will be slightly shorter than the other side. And this is, he said, this is the one is called Bhumi, the other is called the Mukha. And the Parshva, the two sides, the lateral sides, are now all of the same width, he says, because we are working at a small angle approximation, ignore curvature. Now cut out the part outside the altitude. This is the altitude. Now this is for people to get a flavor of how geometry was done actually. Cut this out, then you say turn it upside down, bring it here and put it here. So then you have now rectangle. You know the area of the rectangle. Width times the length. The width is constant, the length varies. Yeah. Think of all the gaps as rectangles. The widths are, etc., etc. Now the method to know how many gaps there are, that is, you count the number of strips, which will be a very large number, and what the widths are, which will be very small, and add them and take the limit. Now, the big change is when he first did infinitesimal stuff, there will be very, very detailed philosophical asides about what is meant by what he's doing. Here, no explanation. Now it's all familiar, open territory. You can just do what you want to do. Just assume that you've understood the general principles, just apply them. When you do it, what do you get? I mean, the modern language, it's very simple. I have this is delta theta. I choose the co-latitude as my angle theta. So this circle, the circumference is r cosine theta. Sorry, the diameter of the circle is r cosine theta. So the circumference is 2 pi r square cosine theta multiplied by the width, which is delta theta, r delta theta, I beg your pardon, r delta theta, multiply them and add them. What does it give? It gives area of the hemisphere is 2 pi r sine theta because that is this radius times r delta theta, r d theta, integrated from 0 to pi by 2. That is 4 pi r square sine theta d theta integrated. Now, today we will simply say the integral of sine theta is cosine theta. There is a little twist there. What they do is 4 pi or 2 pi r square, then integral minus d2 sine theta by d theta 2, because they know the differential equation satisfied by the sine. The reason why this is done is now it's a perfect differential. You take the d out, get rid of the integral sign. You don't have to know. If you know that the sine satisfies this differential equation, and you also know that it comes from knowing that the derivative is the cosine, you prefer to use the differential equation, not the first order derivative. That's very funny for me. So the answer is 4 pi r square, or as they say, it is circumference times the radius. All right, 2 pi r square. This is the hemisphere. The full sphere A is 4, 2, C, R. C is the circumference, R is the radius. That's how it is done. Now, this is exactly how we do it in school, first year college or whatever. You can pull the screen up, huh? Yeah. So, we stop. I want to do this because, this is very straightforward calculus. There is no infinite series, no worries about convergence, no worries about when can I exchange sums, one of which is going to be an infinite sum. No such worries, no such questions. It's just straightforward.
So, when the Greeks did this, how did they do it?
Oh, the Greeks did this, the exhaustion method of Archimedes.
Even for the area?
Even for the volume, even for the area. I think so. Oh, no, sorry, volume. I beg your pardon. I don't know if Archimedes did the area of the sphere.
I think he
Probably did. I'm not sure. But the volume was done by exhaustion. That's for sure. The area was done for the circle by Euclid by the method of exhaustion. So, yeah, so I'm going to stop the calculus part of it at this point, except to say one thing. One of the criticisms made about the Kerala work, the Nila school work, is that if they have only the Maclaurin series, and the sine series they have written down is the wrong sine series. The coefficients are powers of 2 in the denominator. So that they didn't know Taylor series, so it is wrong. It's not calculus. Now, this is, of course, completely unjustified for several reasons. One of them is that the so-called interpolation series is a creation of a student of Yashtadeva, Shankaravariyar, and that derivation is based not on any serious infinitesimal thinking, because it was meant to be an interpolation, just a way of computing angles which lie between two chosen points in the standard division of the circle, 96 at that time. So that's one reason. It was not meant to be a good, analytically correct convergent series. The second reason is, and in fact, Shankaracharya did not do it beyond the third order. He said, we can do it for higher orders if you want the accuracy. Modern writers interpret this that they were trying to get the Taylor series and got it wrong, which is incorrect, because the Taylor series, no big deal for them. I'll tell you why. Because the same Madhava is credited, it's glorified, in fact, not just credited, for writing the addition formula for the sign, apparently, according to the Nila guys, for the first time. That's a historically complicated story, so I won't go into it. So if you take the sign series, the standard sign series, the Maclaurin series for sign, then use the addition formula, sine and cosine, use the addition formula, you get the Taylor series for the sine function, or the cosine function for that matter. So modern historical writing is often muddied by, another point we were talking about earlier, muddied by people coming to hasty conclusions on the basis of insufficient data, or in some cases, insufficient thought. So now, Madhava's other achievements. Now, yeah, I can go here. Most of them have to do one way or the other with the notion of infinity. And the problem of infinity is, according to me, it's not greatly written about in the historical accounts of Indian mathematics, but it is more fascinating, much more fascinating than the story of the zero, which everybody has written about, more or less. And it has a long history. I will not go into the history. I will only quote why it was felt to be necessary and why, what a big role it played in, not in mathematics, but in grammar. There is this wonderful verse, wonderful statement in, Panini, after whom you have named the library here, I was very pleased to see, was a very, very, a truly great thinker. There is no, I've talked to grammarians and Sanskrit scholars and so on and so forth. They say, you ask them, you have very specific questions. What is the basis? All these karakas and so on and so forth, where did they come from? What was the underlying foundation on which he built his approach to grammar? It's very simple. It's naive set theory. Categorical thinking. Turn every object into an element of a category, not in the mathematical sense, but in the common grammatical sense. Then state rules not for individual objects in the set, but for the whole set. You don't care if the set is infinite or not. That is the whole point. In fact, at one point, Patanjali has this absolutely magnificent fable. He says, Brihaspati, the teacher of the gods, was trying to teach this thick-skulled king, the big chief of the gods, Indra, linguistic expressions. Okay, so he did it one after the other, one after the other. At the end of 1,000 years of the gods, they had hardly made a beginning, because language is infinite. And he says, this is not the way to convey the truth of grammatical expressions. The correct way is to have general rules and particular rules. He's very clear. General rules and particular rules. And the person I discuss most with is Fritz Stahl. So I told Fritz, if I say the general rules are rules defining sets, and the particular rules are the rules of operations within the set, would you agree? He said, yes, that's a very good description. So I'm quite happy. So this story is a very long one. It's an old one. That's one way of handling infinity. There is another way of handling infinity, which is recursion. I don't care, you do it for some value of n, do it for the next value of n. If you do it for a general value of n, you've done it for the whole set. Mathematical induction is one example. There are others. And so the reason why recursion played a big role in Indian mathematical thinking is very clear. It goes back to this kind of thought. And the other great thing which these people did, which we don't normally pay a lot of attention to is that the preferred way of proving theorems, positive theorems, not the impossibility theorems, is descent. And that is understandable because, what is decimal numbers come from doing descent on unknown numbers. That is, you take a number, divide it by 10, keep the remainder, divide the result of the thing by 10 till come to an end because the last quotient is less than 10. So that is the model. That is the model which they always had in descent methods. Incredible number of things are proved by descent. Incredible number of things. So there we are. Then the infinity is used also in the getting to the infinitesimal by dividing by large numbers, taking the limit. That we have done enough times. Then, yeah, that's it. Recursion. Yeah, or recursion often leads to formal infinite series. Then you have to worry about convergence, and they do. 2 or 3 examples I've already mentioned, so I will not spend any time on it. The problem with, I go back to the tangent series now because questions of convergence and rate of convergence, they become very important for these people. And as I said, the standard series, the basic pi series, 1 minus 1/3 plus 1/5 and so on and so forth, it's very slowly converging. If you want 2 decimal places, you have to add 50 terms. So Madhava said, what can I do? How can I make it computationally efficient? Because the other big change, very big difference between the Euclidean model, European approaches to mathematics and the Indian approach to mathematics at the highest level is that the Greeks would have said, oh, there is a constant whose value we can only estimate approximately, like Archimedes did. 22 upon 7 is greater than pi, is greater than something or the other. They said, it's not enough. They're very constructive. They want the value of pi. They want to know what precisely is pi numerically. So Madhava wants to compute pi. He wants to know what it is. So what does he do? So this is what I'm going to describe now. Okay? Time is 20 minutes more, a little more than 20 minutes. So what does he do? He says, if I cut the series off at a point j, that is, I can remove this. I can write here. 2 approaches, that is, making the computation of pi efficient. 2 approaches. One is this, right? Etc. Then stop at the term j. I don't know the sign of this term, so I write plus minus j, 1 over j. J are positive odd numbers, positive odd integers. Then, of course, there is a leftover. I call it the remainder, the reciprocal of the remainder, 1 over rj. Then he says, what can I do? What do I know about rj? You know the following thing, because this can also be written as 1 minus 1/3 plus etc. minus plus 1 over j minus 2, the lower odd number, then plus minus 1 over j, 1 over r at j minus 2. The remainder after j minus, when the denominator is j minus 2. So if you compare the two, you find that you get an equation for 1 over rj, or you get a functional equation for rj, and that equation is very easy to derive. 1 over j minus 2, 1 over r of j minus 2, plus 1 over r of j, is 1 over j. It's straightforward. It's very clever, very easy, very straightforward. So what do you do now? He says, I want to solve this equation for Rj. I know it cannot be solved in finite terms, at least I assume that's what he would have said. So I will solve it approximately to better and better accuracy. I want a solution in terms of rational functions. This 1 over, since it comes in the denominator, that's a reasonable thing to do. So he'll do a rational approximation. He will find approximate rational solutions of this master equation. At this point, there is a nice little aside in Yukti Bhasha. About what this means in terms of the notion of a function. Because R depends on J, and J is arbitrary, positive odd integer. Now is the time when I need the screen. There's a very little, a very nice little paragraph in which he says what he means by saying that R is a function of J. Very general. He says, formally, I can solve this equation without respecting the functional dependence by simply saying Rj is 2j, because 1 over Rj, no, sorry. Yeah, Rj, sorry, I'll better write this down. If only Yukti Bhasha says if Rj and Rj minus 2 were equal, and equal to what? 2j, then of course you have solved this equation. That equation has disappeared. Write it down here. Because each of them will contribute exactly the right thing. Half of 1 over j plus half of 1 over j is 1 over j. But he says that can never be. That can never be. And this is what he says. It's a little small part of the quotation. It says it can never happen that each of the denominators Rj minus 2 and Rj is equal to twice the odd number j. Here is why. Suppose the first denominator is double the odd number above it, that Rj minus 2 is 2j, the ansatz I just wrote down. Then he says, second denominator has to be double the next odd number, which is Rj is 2j plus 4. Since it must be expressed in the same manner, or depending on the reading, or following the same rule as the earlier one. Okay, so here is the first conscious, deliberate pointing towards the notion that a function has to be, the functional dependence of the dependence of functions on the variable must be respected. That's the only statement I know in the early literature, Then there is no way in which both the denominators can be equal to twice the odd number. It's not possible. So he says, of course, now in the people sitting here should know, use it as the first approximation. The standard technique of Indian mathematics, use it as the first approximation, look for corrections. That is how the approximate value of the remainder is found. Okay. I'll show you how it works very quickly. First guess, is there anything more after this? I wonder, or we can get rid of it altogether. Yeah, I think it's over. Yeah, that's it. You can pull the screen up. Okay, doesn't matter. So he says, first correction, take R j minus 2 is equal to 2j minus 2. Then, respecting the functional dependence, so I call this R1, if you don't mind, first approximation. Then R1 j is 2j plus 2. So compute 1 over Rj j minus 2 plus 1 over Rj, and you find very quickly that this equation gives us 1 over Rj minus 2. Not that equation, that's what we want, plus 1 over Rj. R1 j is equal to 1 over j plus a correction. The correction is 1 over j. Okay? So if you expand in powers of 1 over j, the first term is correct. That's what you want. Or if you compute the error in R as a result of this approximation, I'll call the error epsilon j, which is 1 over R j minus 2 plus 1 over Rj minus the exact value 1 over j. That is very easily seen to be 1 over j cubed plus corrections. Or you can pull it up there, plus corrections, I don't know. So you have already got rid of the 1 over j. With this correction, you can compute things up to a certain point. Add to the sum up to j terms of 1 over j as the denominator. Add this correction R1, you're already much better off. That's the thing. Then he says, but don't stop there. He says, now, exactly as I got rid of the j term, 1 over j term here, can I get rid of the 1 over j cubed term? And it turns out he can. Okay? And that is done in the following way. Recursive refining, that is. Next. Next step is write R2j 1 over R2j as 1 over the first correction, 2j plus 2, plus 1 over xj. X I don't know. I want to determine x. I have the functional equation out here. Stick this expression back into this, get an equation for x, solve it the same approximate way. The answer you get is solve approximately. What you get is 1 over R2j is equal to 1 over 2j plus 2 plus 4 over 2j plus 2. Now you can easily verify what you've done. The reason why the approximation is designed to kill the 1 over j cubed term. Now the error is proportional to 1 over j to the 5th. This Yuktipasha describes reasonably well, not in a very precise way, but you can follow it. There is no problem. Next, what does he do? He quotes a verse, presumably by Madhava, in which he says, yeah, we want to do better. We want to kill the 1 over J5 term. What shall we do? And Madhava gives a formula for the R3, the next approximation, which is in the form of a rational function of J, which is somewhat complicated. I'm not going to write it out. It's all in Sanskrit verse. However, the great commentators, Ramavarma Tampuran and Akhireswara Iyer, makes a point that this complicated expression is actually the next term in a continued fraction expansion after these two terms. And that is, that's not in Yuktipasha, that whole thing. So one of the things I learned from this is that there was not one line of dissent, intellectual dissent from the earlier things. There were other people who kept alive, because this is not a, nobody says that, no book says that the next correction should be in a continued fraction form. It doesn't say so. So there is a tradition by which people remember that the next term is actually a continued fraction. So when I talked to a Sanskrit guy, then he said, which is easier to describe in a short Sanskrit verse, this complicated formula or a continued fraction with the next term added? He said, the first one is easier because you only have to describe multiplication and addition. Whereas here you have to say denominator of this is this, and the denominator of this is this, and so on and so forth. That expression is, now if you will allow me, I'll be a little lazy, plus 4j plus 2 plus 16 over 2j plus 2 plus other corrections. Now you can check, it's not difficult. You can compute epsilon 3 now, the third error. It is actually proportional to 1 over j to the 7th. It's incredible, because if you now take 50 terms, that is, the error is now of the order of 50 to the power 7, 1 over 50 to the power 7. You get 11 decimal places without any trouble. And Madhava actually gives the value for pi up to 11 decimal places. So that, I think, is how that computation was done. No book says that Madhava used which formula. Okay, so
It doesn't say.
What the dots are, the dots there. He doesn't say. Nobody says what the pattern is. Subsequently, in the 1960s, 1960s, Derek Whiteside claims in a much later blog post that he first worked out the next terms of this. And he gives, but he doesn't say how he did it. Then C.T. Rajagopal and M.S. Rangachari, in a last paper, Rajagopal's last paper on the subject, which is 1984, gives the complete continued fraction expansion. He does that. So it's a very nice story, except that I cannot follow the derivation. I've tried very hard. I don't get it. I tried the standard method, which is that of now, after this, you say it's 1 over y, and it's compute y, so as to kill the j to the 5th term. I got lost, so I said, no, I'm not going to worry. I'm not going to bother. Then the other comment I can make is, this expansion is enough to show in a very elementary way that pi is irrational. If you use reductio ad absurdum, that is to say, the expansion terminates, then pi is rational, then you show that the expansion doesn't terminate. Therefore, pi cannot be rational. Nilakantha has this wonderful verse, not verse, it's prose actually, in which he says that, I mentioned this, I think, that there is no unit which will measure the circumference and the diameter of a circle without leaving a remainder in at least one of them. So they are incommensurable. And he could very well have made this proof, because they were masters of continued fractions. The general technique of repeated, iterated refining, samskaram, it's like bread and butter for them. However, that proof would require the use of reductio ad absurdum. Then Indian mathematics rejected reductio ad absurdum as a method of proof for very complicated philosophical reasons. So Nilakantha, if he had a proof, he would have kept it hidden because he would be going against the orthodoxy. That's my personal take on it. I could be wrong. Could be completely wrong.
The non-termination doesn't necessarily mean.
This particular, there's some properties to be satisfied. This satisfies those properties. It's very easy to see that. It's not difficult. The Legendre theorem, no? That the numerator must be smaller than the denominator. Some such thing. There is some condition. Yeah. Yeah, I knew this at one time. I've forgotten. It's actually very easy to prove. The theorem is easy to prove, not hard. Yeah. So there we are. Now, last topic. One quick remark and then one last topic. The quick remark, 21 minutes I still have? No, that's not possible. That's not possible. You'll have to call an ambulance. So one last remark. One of them is in the process of working this out. This is very general now. J is anything you like. In fact, the book says start J equal to 1. You can do wonderful things. And you get the 1 over R is actually the pi series, you see. Start with J equal to 1. But anyhow, so along the way, they're doing all these manipulations with rational functions. They want to know what it means to multiply two polynomials, to divide one polynomial by another, add two rational functions, finding a common denominator. These are the problems that come up. So Yuktipasha has a little tutorial on what is meant by a polynomial. How is it defined in general? I mentioned it in my first talk. The model was decimal numbers. I have a number n, which I express as an 10 power n plus an minus 1 10 power n minus 1 plus etc. plus a naught. Okay? Where the coefficients ai are in Z mod 10. So this is a principle which was understood already in the Rig Veda, that this is what decimal numbers are. What you're doing is you're measuring a number by using 10 as a standard, as a unit, as a meter stick. Now, Yuktipasha says, but this is exactly what a polynomial is, except do two things. Instead of 10, use any j, j in that context. And the coefficients should be allowed to be any integer, positive, negative, or 0. Then he says, since decimal numbers are written in a certain way, define a polynomial. What is my notation? P as, I'll tell you what these vertical bars mean. A, and that is, polynomial is P of x. Polynomial function is an x power n plus etc. n minus 1, etc. a naught. What he actually says is, draw a line of boxes, compartments, and put the coefficients in them. And he says, be careful. You must not carry over, because when you add, you use mod 10. So when the sum of coefficients or product of coefficients exceeds 10, you have to put 1 here and shift something else somewhere else. Don't do that. He said, just put whatever number you get, put them in the boxes. And this is the object. This is the object which such expressions, a polynomial expression, really means. He says so. Okay? And then he gives many examples, several examples from these problems. Then he says that the multiplication of polynomials is just the standard rules for multiplication of coefficients of a polynomial. Then he says if you get 0, make sure that the 0 is put in a compartment, otherwise You'll get confused if it is not there. And if you get a negative coefficient, put a bar on top of the number, so you know it's negative. It says so. Then, in doing all these things, he said, multiplying coefficients, positive and negative and zero. He begins by quoting Brahmagupta's famous verse, which says, negative times negative is positive, negative times positive is negative, positive times positive is positive. Dhana, runa, something, 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 it goes. He quotes that. Then he's, on that basis, this is what I mean by multiplying two such expressions. This is what I mean by adding two such expressions. This is what I mean by finding a common denominator for two rational functions. So it's very beautiful. What else do I have to say about this? Something else to say on this? Yeah. I'll come closer.
Newton defines power series in one variable.
Yeah.
Says he is influenced by the decimal representation.
Yeah.
And then says these can be manipulated, by which he means added, subtracted, the same way as we do with common numbers.
No, it's much more dramatic than that. Narasimhan, thanks very much for reminding me. What he actually says is, in the doctrine recently introduced for decimal numbers, you can deal with power series exactly as you deal with numbers in the doctrine recently introduced, which is decimal numbers. In fact, the variables are called affected quantities, and he says, more than that, he actually says you can do not only these operations, take square roots. He says that.
At least the one, maybe
No.
the one I know, the main thing is they can be manipulated like common numbers.
Yeah.
For him,
That's it. Absolutely right. Absolutely right. In fact, there is a story about this because, personal story. When I read this, I wrote an email to David Mumford. And he said, wow, he did say that? I said, in a reply, I said, yeah, he did. And he said, I'll go and check. Then he came back and said, yes, I've read it. Then he said, I take back what I said about his being a theoretical physicist, not a mathematician. That's what he said. So it's an amazingly good story, So this is why I said, third lecture, I will be dealing with issues which point towards a certain modern point of view, structural, abstract, and it's very good. Now I'll take 4 or 5 minutes to do something, to describe something which is very clever, which comes out of this thing. What he does is, so having done this, you've cut the series off at one point, then you have estimated the error to arbitrary accuracy, if you like. Now I want to use these results to rewrite the infinite series of I. So what does he do? By the way, he also says that the variable is 1, 0. The Rashi is called the Rashi, a Rupam, is 1, 0. That is x. X is takes the place of 10 in the number representation. So he says x is now represented, the Rashi, the Rupam, what am I saying? Rashi, I beg your pardon. Rashi is represented by 1, 0 in the box. He gives you rules for cancellation in ratios in this form, in the coefficient forms. It's very beautiful. It's about 3 or 4 pages on what a polynomial means. Now, if you want to make accelerating the convergence, rate of convergence of the basic pi series. Basic pi series, I mean 1 minus 1/3 plus etc. You start with the functional equation for the remainder. What is that? 1 over r j minus 1, j minus 2 plus 1 over Rj is equal to 1 over j. Whereas the pi series is 1 over j, 1 minus 1/3 plus 1/5 and so on and so forth. He says, in principle, all you have to do is to replace 1 over j by, if you know a good value for the remainder, you have a good estimate for the remainder, instead of 1 over j, use this. And if you can make the error small in this, if you simply put this here, it will be an identity. There is no content in it because it's always obeyed. So what they do, so exactly how it is implemented, I'll describe it very quickly. I'll define this quantity, I'll define to be 1 over Rj, capital Rj. Otherwise, I have to keep on writing this sum all the time. I'm just repeating what's in Yukti Bhasha once again. Write the series as etc. minus 1 over the remainder at 1 plus 1 over the remainder at 1 plus the remainder at 3 minus 1 over R3 plus R5, etc. Okay? This is a trivial rearrangement in the sense that these just cancel. Minus R1, minus 1 over R1, R3, 1 over R3, minus 1 over R3, and so on and so forth. What you're going to do now is rewrite this series, rearrange it again. This is what I said I would like you to look at in the following way. So this is pi by 4. I write this as 1 minus 1 over R1 plus 1 over, I'll write the whole thing, otherwise people will get confused, plus 1 over R3 minus 1/3. That is, I take this and this and this together. First I group this term with this term, then I group this term with the other two, and carry on like this. Now you can see right away that this is an empty statement because it's always true. Because if I know the R exactly, this is 0. This just defines the first remainder as pi divided by 4, 1 minus pi divided by 4. That's all it does. So it's empty. There's no content in it. But the thing is, if you don't know it very well, what you can do is to try and make this as small as possible instead of just 1 over j. So you've rewritten the series in which the denominators have become much smaller. The assumption is that when you do that, in the limit, nothing changes. You have to assume that. That's what is done. And I'll tell you, I don't want to take too much time. I'll stop here by pointing out two little results. When you do it for R1 and R2, as I've described earlier, the first estimate and the second estimate, you get the following series. R1, forget it, R2. You get pi divided by 16 is equal to 1 over 1 power 5 plus 4 times 1 plus minus 1 over 3 power 5 plus 4 times 3 plus 1 over 5 power 5 minus plus 4 times 5, etc. Okay. This, Tambiran and Iyer have used this series to estimate pi. You get 50 terms will give you, as you expect, 11 decimal places, 12 significant figures. Yeah, 50 terms. And then subsequently, after Madhava's time, 1800, around 1800, there was the last descendant of the school that we know, who was a prince in North Kerala, actually very close to, maybe 10 kilometers from where I was born, who wrote a book called Sadratnamala. And in that, he takes a little more trouble, and he has pi up to 18 decimal places. So, so it's a very constructive approach to mathematics. So the technical part of my talk is over. I will conclude by reminding everybody of the beginning of the story and make a few remarks about the end of the story. The beginning of the story we have already seen. Unfortunately, I rushed through those last slides, which I wish I had more time with. The beginning of the story is that there was this family, Embrandiri family, who came to the valley of the Nila from the country further north, about 200 kilometers further north, Karnataka, across the Netravati River. They came here, settled here. They got the name Embrandiri because they came from Tulunadu. Then he comes and he gets a student. His name is Parameshwara. Parameshwara is the grandson of a person whose name we don't know, who was a student of a very famous person, very famous astrologer. His grandfather, Parameshwara's grandfather, was his student from Alathur, which became the focal point of all mathematical activities in Kerala. And that person was called, what's his name? Oh, anyhow. Oh, I have it somewhere here, maybe. Talakkulam, Talakkulam Govinda Bhattadari. He was a very famous astrologer. And this line, the astrologer line, is the direct continuation of the first Muziris school, that is Govinda Swami and Shankara Narayana, who brought the teachings of Aryabhatta to Kerala through the writings of Bhaskara I and Shankara Narayana, who then wrote a book in 869 in which the Aryabhatan method of astronomy and some of the mathematics is described. That line became corrupted very quickly by astrology. And there's a couple of very good people. One of them, a man called Surya Deva, very good astronomer mathematicians. Another was called P P Divakaran. And so it's a well-known line. However, Alathur became a center of astrology. And it still is. It is the place where Jayalalitha used to go from time to time to consult the Kanippayur family of astrologers. And from where she took people to officiate in a temple on the way to CMI in Chennai, on the left of the East Coast Road. So it's a very long line of this kind of activity. Okay, Sri Lankan chief ministers and prime ministers and presidents used to come to Alathur to pray there, for the blessings of the. So if you go now to Alathur temple, you say, I want to come to see the Ram temple, Sri Rama temple. He'll say, sir, don't waste your time going to Sri Rama temple. He has no power. You go to the Hanuman temple. Okay, you go to the Hanuman temple, and a good day, if you're lucky, Hanuman will be wearing a silver crown. And the silver crown was one of the offerings of Jayalalitha at that time to Hanuman. She used to go to worship there. So it's a very nice story, very human. However, he was lucky to have Parameshwara as a disciple who already had a background in astronomy. And then came this incredibly gifted line of mathematicians and astronomers. And it's a very good story. I mean, it's one of the examples I know of a long-lasting, very coherent, ideologically and intellectually coherent line of people, all very gifted, carrying forward a wonderful legacy. How did it end? Well, there are several things which contributed to the end, according to me. One is the depletion of the Brahmin population. That is to say, there was a time when the population of Brahmins in Kerala was estimated, that is 1300, around 1300, to be estimated to be about 20 to 25% by a very reliable historian. I trust him. However, 1881 in the census, they're 2%, the less than 2%. So what happened? Several things happened. One of them is that they got into this extremely obscurantist way of obscurantist marriage customs, by which only the eldest son could marry a Brahmin woman and beget Brahmin offspring. So the relative proportion, you produce not enough male descendants of the same caste. So they little by little, they disappeared from the scene. And if you look at the line of mathematicians and astronomers that I wrote down on the first day, you would have seen the last two were not Brahmins. They are, from their names, Warrior and Pisharadi. You know that they are males whose fathers were Brahmins, but the mothers were not Brahmins. So that's one of the things that can be. They ran out of students, which is happening in Kerala now. They're shutting schools there. There's not enough kids. So secondly, there was an absence of fresh blood. There was no more migration. 1300, the migration from northeast stopped. Nobody came to Kerala after that, or very few people came to Kerala. That's the other thing. And the third thing is the immediate trigger was the Portuguese invasion. The Portuguese came and bloody fighting took place in the same villages, in exactly the same places where the mathematicians were living, because it's very close to the sea. The Portuguese had built a fort. The Zamorin was fighting them back. There was a lot of bloodshed. So that's it. Besides, the Zamorin, who was the patron, who supplied the funds, supported the DST of the times, or DA, maybe I should say here. They ran out of money. That's how it ended. Thank you very much, all of you.
Thank you very much for that very nice set of lectures, which I think a lot of people will not only view it, not leave it here, but I think a lot of people are already viewing it on our YouTube channel. So any quick questions?
So there is an important equation you wrote down, n equal to this decimal expansion.
Yeah.
That equation goes back to Aryabhatta.
No, much earlier.
Much earlier, right?
Yeah. The principles of decimal enumeration have been mastered by the time the Rig Veda was written. I'm very proud of saying this loud. I actually wrote a very long, the most difficult paper I've written down is to analyze, along with someone, Bhagyashree, no? You met Bhagyashree. Bhagyashree, my collaborator. Yeah, the two of us, she's a Sanskrit scholar. We read the Rig Veda, found all the number names. You won't believe it. Rig Veda is supposed to be a religious text. There are 3,000 names of numbers in it. Construct complicated numbers constructed following grammatical rules, which we translate back into rules for multiplication and addition. And then you know that they knew, except nothing was written down. 100 was not written 100, but it's given a name, Shata. Then you have to combine them grammatically. So, yeah, Rig Veda. That is, I agree with you, the most important equation. Yeah.
One more question. So all this mathematics in terms of words and poetry and singing is not the way we do mathematics.
No.
Right? So some other civilization.
Yeah.
Is it Al-Khwarizmi and the Arab
Arabic
school in Baghdad or Damascus?
Yeah, I have to apologize for the fact that my knowledge of the Baghdad school of science, especially mathematics, is not very good. It's very poor. I don't make any comments on it. I have tried whenever I can to compare it with early Mesopotamian mathematics, Babylonian mathematics. They are very, very impressive. But I have not followed the Egyptian pre-Mesopotamian mathematical ideas. It's very difficult because the sources are extremely vague. You cannot really draw any reasonably sure conclusions. And surprisingly, that is true of Chinese writings on mathematics. It's all word of mouth. That is to say, you'll find a text, 1st century AD. I mean, this guy, what's his name? Dobbin. What Dobbin? Joseph Dobbin. He will write that, this is the text from which we know these things. What is this text? This is supposed to be a commentary on a text written 500 years earlier. Nobody knows what that text is. So I keep away from Chinese mathematics. I just don't know enough. But the Baghdad school was terrifically, very imaginative, very productive, very, very good, very creative. I don't know much myself.
I was only asking about when did the way you wrote these equations.
Yeah.
How did that come about? That's a big jump.
Oh, this kind of thing?
Yeah, it's not in words, it's a formula.
I have converted the words
I
into
understand,
formula.
but you have converted it into a formula based on your studies of formula in the past.
I do this only because I'm communicating with people.
He's asking the historical origin of
Notation.
algebraic notation.
Symbolic notation.
Symbolic.
That is Greek.
But for
Euclid already had diagrams with points labeled by letters.
That was before Madhava, but then what happened?
Madhava's work, we only know it in prose. Only know it in prose. Now, we who would like to, it's like it's a new skill. It is like learning a foreign language. When you read these prose texts, I gave that one quotation remember, on the sphere. I did this so that people get an idea of how abstract things are described. But geometry is not very abstract. Algebraically, he will say, take this number, add this, multiply this, or take this formula. Or the technical terms will do part of the work for you. Like, for example, the variable will have a name, a sum of, for example, when you want to add 2 or 3 quantities, finite number of quantities, there is a word for it, which is called yoga, joining together. If you want to then add n such terms and take the limit n going to infinity, then they will change the word now from yoga to samkalita. So that, other people tell me that's how one should read it.
Also, like when you said about people calculating, I'm sure when they actually calculated, they must have
written things down.
To 55, when you have to sum up to 55
At a certain
terms.
point, Rajesh, because it's actually not very difficult to do basic arithmetic without writing things down. It's not difficult. I have actually given lectures on how to do that, but anyhow. But certainly from the time of Aryabhata.
Go to 11 decimal places, I don't know.
No, this is much later. They really had to write things down. They couldn't have done it otherwise. Yeah. And the numbers themselves will be described in very figurative terms. For example, the 11 decimal place formula of Madhava, it will use a mixture of names like Kharva and Nikharva, which are names of powers of 10. Then it will use Bhuta Sankhya, which means you make a one-to-one map between sets which have a certain cardinality and the corresponding number. Like if you say Bahu, that means 2 because we have 2 arms. Or they use Katapayadi, which is a more abstract way of describing numbers. But they definitely had writing, there is no doubt.
Also, they used sometimes astronomy, right? 27 stars.
That's Buddha Sankhya. Yeah.
They use that as well.
Yeah. So, thank you all again.
Okay, thank you very much.